Ask a room of researchers what a p-value means and you'll often get a dozen confident, subtly wrong answers. It sits at the heart of statistical significance. It decides which drugs get approved and which experiments get published, and yet it is one of the most misunderstood numbers in all of science. Today we're going to nail down what it really is, what it absolutely is not, and how misusing it fuels the replication crisis. Let's get it right. Let's start with the question a p-value is quietly trying to answer, because the framing is everything. Imagine you run an experiment and see a difference. Version B outperformed version A, or the treatment group improved. The raw question is simple but treacherous. Is that difference real? Or is it just noise, the kind of wobble you'd expect even if nothing were actually going on? This is exactly the gap a p-value tries to fill. It asks how likely your observed data would be if nothing real were happening, if the effect were pure chance. Rather than proving anything true, it measures how surprising your result would be in a world where the effect simply does not exist. So how do you actually use one correctly? Let's walk through it as a careful, honest procedure, one step at a time, because the logic runs backwards from what most people expect. Begin by assuming the null hypothesis, the boring baseline that says there is no real effect. The drug does nothing, the two versions are equal. You temporarily grant that nothing interesting is happening, and then you ask what your data looks like in that world. Then compute how probable your observed data is under that assumption. Specifically, the probability of seeing results at least as extreme as the ones you actually got, purely by random chance. That probability is your p-value, and it lives entirely inside the null's imagined world. A small probability, say below 0.05, means your data would be very unlikely if nothing were going on. That counts as evidence against the null, and we call the result statistically significant. A large value means your data is quite consistent with pure chance. Finally, and this is where people go wrong, pair the p-value with effect size and confidence intervals. Never treat 0.05 as a magic truth line. A tiny, meaningless effect can cross that threshold with enough data, so significance alone tells you almost nothing about importance. Now let's lock down the three things about p-values that trip almost everyone up. First, the real definition. A p-value is the probability of data at least this extreme, assuming the null hypothesis is true. That conditional framing, assuming no effect, is the entire subtle point, and it is what most casual descriptions quietly get backwards. Second, what it is not. It is not the probability that the null hypothesis is true, not the probability your result happened by chance, and not a measure of effect size. Confusing any of these leads directly to overconfident, wrong conclusions about your experiment. Third, how it gets abused in practice. Testing many things until something finally crosses the line is p-hacking, and treating the arbitrary 0.05 threshold as a hard magic boundary distorts entire scientific fields. That kind of misuse is a major driver of the replication crisis we hear so much about lately. Alright, let's lock in the four things worth remembering. The number itself is the probability of data at least this extreme, computed under the assumption that the null hypothesis is true, and getting that conditional framing right is half the battle. It is not the probability that the null is true, not the chance your result happened by luck, and not a measure of how big or important the effect is. The 0.05 threshold is an arbitrary convention, and treating it as a magic truth line invites p-hacking. Best practice pairs the p-value with effect size and confidence intervals for an honest picture. If untangling ideas like this is your thing, Standarity.com is full of plain language explainers. See you over there.